Good morning, everybody. If you have any questions, short ones, just let me know in the chat or use the mic. Good morning. I have a question. Do we call it kernel or the null space? Yeah, so null of the, we'll talk about it, but yeah, null of the linear transformation. So, we'll come back to this, like rank nullity theorem, stuff like that. So yeah, where the transformation is zero, null. Like, let me see something. So, right. So usually from what I see, null space is for, it's the same thing. It's where the transformation is zero, but null means zero. I see. Yeah, it's fine. Use either one. But I think the book uses kernel, right? So let's follow the book. Now I usually seen it for matrices, but yeah. All right. Well, so let's do that. So yeah, last time we let's see. Yeah, so last time we finished the transformations. Let me define here kernel and image. So for a linear map, T going from V to W, we define kernel of T to be all the vectors in V, so that TV is equal to the zero vector of W, and image of T to just be the all the W's in W, so that W is equal to TV for some V in V. All right. So the picture is as follows. This is your V. And there's a little pocket around zero called kernel of T. And this is W. And this pocket gets sent to the zero element. And all the other stuff gets sent to the image of T. Okay. And right. So there's stuff that does not get caught by T. Okay. I should write some stuff here. So when kernel of T is just the zero vector, we call T injective. Okay. And when image of T is the whole space, we call T surjective. Okay. Is that okay? So, yeah, so injective, just to remind you, there's an equivalent property. So injective means also means that if X is not Y, then T of X is not T of Y. Okay, so let me show you that this is equivalent to having the kernel being just the zero element. So assume by contradiction that tx is ty. Okay, then you use linearity, so you have tx minus ty is equal to tx minus y equal to 0 w. But then that means x minus y is in the kernel of t, which is just the 0 guy. And so that means that x is equal to y plus 0, right? V, which is just y. So x is y, which is a contradiction. Okay. So injective is the same as saying that the kernel of your linear map only has the 0 vector, and surjective means what we wrote here. So you give me any w, so any w in w, I can always find some v to map it to. Okay. All right. Let's go. Let's do some examples. So the easiest example is the regular linear maps, so lines. So it sends x to ax plus b. Wait. So x is 0, then y is 0, you get minus b over a. Right. So let's find the kernel in image. So kernel of this guy is where you have this ax plus b to be 0. So you just isolate for x, right? So you get that the only x where this is true only happens at one point, only one element. Now, let me make a point here that, so I should say this. So this is a linear map only when, so let me write like this, because, so for maps given by this, we have this, but this is only linear. Hopefully someone mentioned that. Okay, I'll say it. So this is only linear when b is 0. Okay. Does anybody know why you only have linear only in this case? Any guesses?
If
yes?
t is not 0, then there's going to be no additive identity.
Yeah, actually they both fail, right? So tx plus ty is equal to ax plus y. This is fine, but then you get 2b, and this is not equal to tx plus y, because this guy is equal to ax plus y plus a single b. So, right. Yeah, so you only have one element, and so you always get the 0 guy. So you will get the 0 vector. And so now using this, let me mention the following. This is a proposition. The 0 vector is always in the kernel of linear maps. Okay, so the kernel is non-empty of a linear map. And yeah, let's prove that. So, so you have t of 0v is equal to 0v plus 0v, right? Because 0v is an additive identity. And then you use linearity. So you have 2 times, or let me not write 2. Let me just say T0v plus T0v. And then you add the additive inverse to both sides. So you have, you know, 0w is equal to T0v minus T0v, which is equal to T0v. So you got that T0v gets mapped to the 0 of w. All right, so is that okay? So you always have, yeah, you always have the 0 element in your kernel. So even though these guys look linear, they're not linear only for b equals 0. And yeah, so the image of these guys will just be all the ones that cross the origin. Yeah. Where else? Okay, so let's see. Right, so we studied this map before. Let me take you there quickly. So we had this map over here, and we evaluated at the basis, and we found a general formula for it. So we found that if this guy maps 1, 1 to 2, 0, minus 1, and 1, minus 1 to 0, 0, 1, then you can find the general form of this vector. So this is a linear map. So it has a kernel and an image. So now we're going to find its kernel and image. Okay. So by kernel, what do we mean? We mean that this a plus b 0 minus b gets sent to the 0 vector of R3. So this is the 0 vector of R3. And yeah, so this is the 0 vector of R3, but then you just do vector component equality. So this is the 0, 0, 0. So you get a plus b is 0 and minus b is 0. So you get a is minus b is 0. So you get that a is equal to b is equal to 0. Yeah. And in terms of image, again, you take arbitrary element of R3 and you ask, can you find a plus b and minus b to get this element? Well, the answer is only when y is 0. So if y was not 0, the answer is no. Because you can see that you have x, y, z is equal to a plus b, 0 minus b, but this forces y to be 0. So, but for the other guys, you can do it. You can take b to be minus z, and then you can take a to be what do I want? X and plus z. So you define your b to be minus z, and you define your a to be x plus z, and this will give you this. Is that okay? Oh, question. Sure, I know we used it in class before, but I'm confused. Why intuitively we can go from 2 space to 3 space? Why? Oh, let me see. What do you mean? I mean, you can see here that we're not really, we're still in 2 space, right? So your intuition is correct. We were not able to fully cover all three coordinates. We lost the coordinate. One of the coordinates is forced to be 0. So in a way, we're still in 2 space. So let me draw a picture here. So, I mean, I don't know how I'm gonna draw this, but let's see. So this is R2, and your guy gets mapped to R3, but this is X, this is Y, this is Z, but then the Y is always 0. So if you give me some curve here, it gets mapped in a flat way over here, but it's like flat. It's still flat. So let me do this in red. Right? So this is R3, but T still sends 2D to 2D. You can't do anything more than that. That's right. Yeah. So we're not adding, that's right. We couldn't. I mean, there are examples. So what is it called? So, but there is a way to do it. So if you're interested, it's called piano curve. And even a thing called Brownian motion from probability. It can send R1, so time. You can send it to a space filling curve. So they go under the name space filling curves. So they do exist, but they're not linear maps. They do all kinds of crazy behavior. So for linear maps, the answer is no. And I think you can try to prove that you can really go from lower to higher dimension and feel it. But there are examples. Is that okay? Yeah. So good. So yeah, Brownian motion is very beautiful. It shows up all over the place. I study it in my own research. It's amazing. Because it's like central limit theorem for curves. All right. What's another linear map? Yeah, the derivative. So this guy acts on the space of polynomials. What do we mean by that? So take P of X to be a0, a1x, a2x squared, so on, an xn. And when you act with dp, well, what's going to happen? It's going to kill the constant terms, and you're going to be left with a1x, 2a2x, oops, this is should be 1. Then 3x squared, and then n x n minus 1. So you went from a pn polynomial to a pn minus 1 polynomial in R. So that's the derivative operator, okay? And we will talk about it next week, Zoom or in person, wherever you are. You can identify polynomials with the vector tuple of their coefficients. And so D sends this guy to the tuple. So D sends it to, what is it? Yeah, let me write this one. No, I'll write that one. So A1 to A2 N A-N. This is in Rn. This is in Rn minus 1. You can see it that way, or you can even add a 0 here just to make it nicer, like that. So it shifts down. This is another way to think of derivatives. So we'll come back to this identification called coordinate map. And it basically sends every vector space to Rn. So if your vector space has dimension n, it will map it to Rn. This is Rn plus 1, by the way. Okay. So this is another way of looking derivatives by treating the process of differentiation as a linear map. Yes. So the derivative is a linear map, and if you do any multivariable stuff, like in 237, they will talk about that. Like the Jacobian is the matrix representation of the derivative. So Jacobian is the matrix representation. So there's many stuff here. Yeah. Power. Yeah. Okay. Let's see. So we have to find its kernel and image. What's the kernel? Well, all the polynomials that get sent to 0. So dpx equaling 0. Well, from first year calculus, these are just the constants, right? So d of p0 with no x's is 0. So p will just be so p of x will just be the constant polynomial. So that's the kernel. And now what about the image? So the image says, find me all the q that can be obtained from the derivative of a p. So I wrote them here specifically. So you give me some q, I need to find you a p. Any guesses what the p will be? Like the coefficient? So p of k will be what? Qk times what? What do you think? Any guesses? So that you will have dp to be q. Think of integration. No? 1 over k. Anybody else? No? All right, let's see. So, right, yeah, so it's 1 over k. And how do you do this? Well, you have dp is equal to summation of qk and over k dxk, and then indeed you get qkk k xk minus 1. Oh, and you have to also change the coefficient, so it needs to be down like this, qk minus 1. So yeah, you get qk minus 1 xk minus 1. Right, so let me do a middle like the first one, I guess. So d of q1 2 over x squared will give you q1 x. Okay, so that's the one of the terms for q. So you started with this p guy and you obtained a general q. So you started with some guy in pn and you gave me an arbitrary element of pn minus 1. So that means the image of t are all the n minus 1 degree polynomials. So pictorially, you have pn, and you have Pn, and inside it you have Pn minus 1. So this map will send everything to you know, the Pn minus 1 guys. And internally, you have the constants. So this guy sends, oh no, I should do it the other way. So this is the 0 guy, 0 polynomial. And here you have the constants. So it sends all the constants to 0. And it sends the entire space to Pn minus 1. So this is the image. And the kernel gets mapped to the constant. Okay. Is that okay? We don't need the 1 though. The 1 was a choice. We don't need the 1. What? Let me see. What are they talking about? The 1. Oh, did I write 1? Why did I write 1? Oh yeah, you don't need the 1. Yeah, that's right. Because you take a derivative, so you kill it. In fact, I don't even know why I wrote 1. I could have just written 0. It was unnecessary. Yeah, thank you. It could just be 0. I don't know. Right, so then it's not injective. So thank you. So that's why this 1 is irrelevant. Good point. Let's talk about this. That's a nice one. So what do you guys, okay, I mean, I already answered. So it is subject. So just a second. So it's neither. Okay, so it's not surjective because image of T is Pn minus 1, which is fully contained in Pn, right? So it's not surjective. And it's also not injective because D of 1 is equal to 0, which is equal to D of 2. But 1 is not 2, so not injective. So neither. Is that okay? Okay, good. Maria, is that okay? Okay, good. So yeah, neither. Different elements get mapped to the same guy, different constants, same 0, and the image misses elements. So namely the, which one? So what am I trying to say? So yeah, if you give me like, I don't know, P equal to xn, or Q maybe to xn, Q equal to xn, there is no P in Pn such that, you know, dp will equal xn, right? Because this guy is at most nth degree. So when you act with the derivative, you will kill the top degree. So you can never get this. But okay. All right. What else? So yeah, that's the polynomial. So, but at least you identify the image. The image is exactly all the n minus 1 degree, not the n degree, but the n minus 1. All right, let's prove some stuff now. Do some proofs. So the kernel and the image are both subspaces. So closure, you have closure. So if two elements are in the kernel, their sum is, and their scalar multiples. So yeah, let's do kernel first. You give me any element of the field, and 2 elements of the kernel. Just to remind you that for both subspaces, for both vector spaces, we take the same field. Take same field. Otherwise, scalar multiplication is meaningless. Scalar linearity is meaningless. Doesn't work. Okay, you cannot do TAV equal to ATV. This guy is an element of V, but this guy is an element of W. Anyways, just to make sure you don't make that mistake. Okay, so yeah, this is easy, right? So you use linearity on the first step. But then you know that both of them are sent to 0 because they're in the kernel. X, Y are in kernel. So, and then you have additive identity. So you get the 0 element. So indeed, AX plus Y gets sent to the 0 guy. All right, so now for image, what do? You take 2 elements and you want to show that BZ plus BW plus Z is also in the image. So that means, yeah, so these guys are in the image, so you can find some X and Y. All right. So we have to do the same. So now we do linearity in reverse. So we know that W and Z are in the image. So you can replace them by TXTY. And so you can write their summation as T of some other summation. So indeed, given BW plus Z, we can find sum H equal to BX plus Y, so that T of H is BW plus Z, which is exactly the definition of being in the image. Okay, that's the definition, that you can find some element in the domain. Okay, all right. Oops. All right. Yeah, okay, so these are subspaces, the image and kernel. And for now, we will talk about their spanning, their basis for the kernel, but now let's just do the image like in the book. So the claim is that if you give me any basis, any spanning set for V, you can obtain a spanning set for the image. Okay. So let's do that. So first we show that one inclusion, you can include the image in the span. So what do? You take an element in the image and you want to show that it's included in the span, right? So give me any W, then you can do that. That's what we want to show. All right. So since W is in the image, there exists some X so that this is true. But then X is in the vector space V, which is equal to the span of V1 to Vn. So you can find some linear combination for X as a step 1. Okay. But then you use linearity for T. So what does that mean? It means that W is in the span of TV1, TVN, right? Is that okay? Yeah, so you get W is equal to a linear combination of the vectors TVN to TVN, and then you reverse the steps. So I think I wrote it over here. You give me any arbitrary element of the span. So this is arbitrary linear combination. And then you use linearity. But then by definition, this is an element of the image. So indeed, you get that any arbitrary linear combination can be put inside the image. So that shows that the span of TV1 to TVN is fully contained in the image. So you get both inclusions. So together you get equal. Okay, so that's another way to think about the image, that you can just span it by your vectors. So yeah, let me do an example here. Or do I have a better example? No, let me do the derivative one, which is nice. So can someone tell me what's the basis for Pn of R? Can I see somebody? What's the right? So perfect. Thank you. Thank you. So you have all these guys, x to xn. Now, so can somebody tell me what would this get mapped to? So what would be TV1, TVN when t is the derivative operator? So this will be what? This should be easy. You can just copy paste what you did. Perfect, thank you. So it will be 1 all the way to xn minus 1. So, and you should put some numbers here. So this will be n, this will be 2x, and so on. But these coefficients are irrelevant. So span of 1, 2x, all the way to xn minus 1 is equal to the span of 1x all the way to xn minus 1, which we already know to be the n minus 1 r. So this is an alternative proof that the image of t, so this is the image of t, right? That the image of t is just the Pn minus 1 of r. So this is an alternative proof. And the core step was over here. We used our little proposition. From there, we used the span that you can change the coefficients. Is that okay? All right. Hopefully that's clear. So that's another way to quickly compute what the image would be. Yeah, if I think of something else, I'll tell you. But yeah, good. All right, so let's play with this stuff. Another way to use this is we can give you some general set, and then we need to figure out some linear map to help us compute this to show like this is a subspace. right? Because convex linear combination. No, it's not. You need 1 over lambda for that. So let me say it this way. Suppose we give you some set L and you show that it's equal to the kernel of some T. Then you immediately get subspace, because we already proved closure for linear maps. So you don't have to show closure for the subspace if you can prove this. Okay, so that saves the work of showing closure. But then the work is trying to find this map. But often it's obvious. So in this case, like we will do examples and you will see and get a handle of it. So in this case, we use what's called the evaluation map. And this guy takes a polynomial, a0, a1x, xn, and it evaluates this polynomial at 1. Okay, so px at x equal 1. So you just get these coefficients. And the subspace says, okay, set all these coefficients to 0, right? So it says compute the following guy. So take, let me write this way. So this guy is all the polynomials such that T1 of P is 0. But what is that? This is just the kernel of this map T1, right? Let me ask you another question. What if L was same thing, a0, a n xn, and suppose I wrote, let me see, yeah, let me say ak 1 over 2 to the k equals 0. Can you tell me what's the evaluation? I don't know, it's kind of obvious, but I just want to see for following. So what would be this would be the kernel of what map? T at what? Right? Okay. Hopefully this is obvious. So yeah, it's the half, right? So stuff like that. And now what's the difficulty here? The difficulty is you need to show linearity, which is kind of the same of us showing closure. But I don't know. Okay. But you can see here showing closure could be a little bit annoying, right? It looks the same actually. All right. So you just need to show linearity of this map and then use your result that kernel is a subspace. So what does this guy do? It takes 2 polynomials and he maps them to their coefficients. It evaluates them at x equal 1. So this is the first step. And then you use linearity of the sum. So there's nothing new here. And what else? But these are just the evaluations of the polynomials individually. Okay, so, and which is just the map T1. All right, so maybe the first step is tricky, but all we're saying is write it as CP0, Q0, and CP1, Q1X, all the way to CPN, QN, XN. All right. How did we get CP1, Q1? Right. So this is because P1 is simply this summation, K0 to N, PK. So let me write the middle step. So P1 is equal to P0 plus P1 to Pn, which is just its summation. So P1 is the evaluation at x equal 1, which is this. Is that okay? Okay, great. All right, so that's all you had to do. You just had to show linearity and you're done. You got that L is indeed a subspace. All right. So then I have another example. And then what? And then we'll talk about composition a little bit. All right. Okay, so again, here's another annoying example. You have this and you want to show is a subspace. So what could be a map? TA equal to what? That could give you that this is the kernel of this map T. What do you think? I mean, if you have the slides, it's sort of easy, but the book shows linearity using CP plus DQ. So yeah, you can just use this because yeah, you can follow the CP plus Q. It's fine. So any ideas what TA will be without looking ahead in the slides? If you know any ideas. So I want to write this set of matrices where A is equal to A transpose. So just to remind you, A, B, C, D transpose is equal to A, D, B, C. Any ideas whose kernel this set is? LT of A. Good. Yeah, thank you. Perfect. That's it. So you just take this guy, AAT, and you see that this guy says all the matrices so that AAT is 0. So TA, which is the same as this map here is 0. So okay. And yeah, I want to do it both ways. So one way we'll do it with this kernel, and another way is with the image. All right. So yeah, here we're working with real matrices. So transpose is the one I just described. So yeah, let's see. Let me do it here. So CA plus B. This guy is the CA plus B plus CA plus B transpose. But transpose is a linear operation. So so you have still this CA plus B, and this guy becomes CA transpose plus B transpose. So transpose is linear. So this is from previous courses. If you wanted to show this, you will have to work with the, you know, that adjugate transformation. So, but yeah, let's not go into this. So at least for 2 by 2, let me just do the simple case. So let's do something simple. Suppose you have A prime, B prime, C prime, D prime, and you take a transpose like this. Then you can still split this into 2 matrices, right? Component wise. So you get your A, C, B, D, and your C prime, A prime, C prime, what is it? B prime and D prime, which are A, C, B, D transpose, A, B, C, D, transpose. For the general dimension, you have to use adjugates, so it's a little bit messier. And so you indeed get CA transpose. And of course, you're free to use this transpose as linear result. And what else? And then B transpose. So CTA plus TB. Okay. So in this first conceptual step in solving this problem is finding the expression such that is equal 0 and then sending them to the map. Yes, so that's the hard part, to find this map T that will give you the, oops, that will give you kernel of T. All right. So I did it another way with the image. You can work through it if you like. So, but I shall stop here because we're out of time. So thank you. Yeah, you too. Right. So in this example, it's pretty straightforward. We just move minus AT. I will have to think of one. I mean, yeah, we will, I'm sure we will come back to it. If you think of an example, please let me know. I'll be happy to, so far the ones I've, thank you. Okay. I don't see any, if anybody has a question, the two of you can let me know. Otherwise, no? Okay, all right. So see you on Zoom or in person next week.